It's a great pleasure and an honor to have today with us Professor Dimitri Bertsekas, which is a professor at the MIT, and this is part of the KIOS Distinguished Lecture Series, and in fact this is the first such lecture as part of the Distinguished Lecture Series, so it's very appropriate, I think, to start the Distinguished Lecture Series with such a prominent researcher and an academic. Professor Dimitri Bertsekas did his undergraduate studies at the National Technical University of Athens in Greece. He obtained a master's degree in electrical engineering at the George Washington University in 1969, and his PhD from MIT in 1971. After that, he held faculty positions at the Stanford University and University of Illinois. And since 1979, he has been teaching at the Electrical Engineering and Computer Science Department of MIT, where he's currently a McAfee Professor of Engineering. Professor Bertsekas, as many of you know, is world known for his research and for his teaching and books. And he has received many awards, including the Inform's 1997 Prize for Research Excellence in Interface between Operations Research and Computer Science for his book Neurodynamic Programming, which was co-authored with Yannis Tsitsiklis. The 2000 Greek National Award for Operations Research, the 2001 John Ragazzini Education Award, the 2009 Bellman Control Heritage Award, and these are some of the most prestigious awards in our field. In 2001, Professor Bertsekas was elected to the United States National Academy of Engineering for pioneering contributions to fundamental research, practice, and application of optimization/control theory, and especially its application to data communication networks. So it's really a great honor to have him here with us today. This is his first time in Cyprus, and he will give a 3-hour lecture, which is not all 3 hours of today. So half of it would be today, and the other half would be tomorrow at 11 o'clock. This is the topic of his lecture on approximate dynamic programming. I think it's a very timely topic. It's a very important topic in optimization and in some of the new developments that are going on in machine learning and in automation. So this would be very useful, especially for some of the young researchers at the University of Cyprus. So I'd like to ask Professor Bertsekas to give his lecture. Thank you.
Thank you very much, Marius. It's my pleasure to be here. My lectures are going to be on optimization by dynamic programming and the use of approximation, with the idea of being able to address large and challenging problems that perhaps cannot be addressed in any other way, and in a variety of practical contexts. This is a hot field, and it has been for the last 25 years at least, and it's picking up in importance in view of improvements in computational infrastructure that are available. So what we are going to do in these two lectures is first start with exact dynamic programming to set the stage, and then we will focus on approximate dynamic programming for optimal control problems under stochastic uncertainty. There are other problems that can be addressed with the same methodology, but we'll focus on standard optimal control problems with stochastic disturbances. A very broad subject, rich variety of theory, algorithms, and applications. The applications come from a vast array of areas: control, robotics, and planning. That's one area where the field has originated from. Artificial intelligence is another somewhat starting point for the field, and the applications go into research, economics, and so on, even combinatorial optimization. We are going to focus on discrete time systems. The field is vast. We're going to carve just a little piece of that and then build on it, and I give pointers about possibilities and extensions. So we focus on discrete time systems, mostly for a finite number of stages, a finite horizon. These are easier problems. And we're going to use the expected value criterion, and we're going to focus mostly on algorithms, less on theory and modeling. A lot of things that we're not going to cover. Infinite horizon problem is another major part of this field, but we're going to cover it only briefly. It has a richer theory and mathematical underpinnings. We're not going to cover imperfect state information problems, problems where the state of the system is not observed exactly. Imperfect state information problems can be formulated into the kind of problems we're going to discuss that involve perfect state information, but this transformation is somewhat complicated and also complicates the algorithmic solution, and we're not going to get into that. There are applications in minimax problems, sequential game problems. We're not going to cover those. And now there's a lot of literature that you'll find discussed under the names neurodynamic programming or reinforcement learning. Neurodynamic programming is the title of my monograph with Johnson Sickness that Marius mentioned. The title suggests a marriage between dynamic programming techniques and the technology of neural networks. And in large part, and this is a realistic subject, particularly these days where neural networks have become. The artificial intelligence name is reinforcement learning, and it's very hot today, particularly in view of very prominent successes that have been achieved. You may have heard about the AlphaGo program that it was a program that learned how to play Go at the level to compete with the best humans, and it is based on this methodology, and the people who developed it come from the artificial intelligence side of reinforcement learning. However, the methods that were used there are going to be touched upon in this lecture, but not fully. There is a series of video lectures on infinite horizon problems and simulation-based methods that you can find links to from my website. So my lectures here are going to be complementary. These lectures are going to be on finite horizon problems. The other lectures that already exist in the internet are for infinite horizon problems. And this is a reference. I have a 2-volume book, and the latest edition of volume 1 was published a few months ago, and my lectures are going to follow chapters 1 and 6 so there's pretty good documentation of this material. Okay, so what do we plan to do? First, overview exact dynamic programming, the basic problem that we are addressing, some examples, then develop the dynamic programming algorithm for finite horizon problems with perfect state information. And that will give us the opportunity to discuss the computational limitations, why we go into approximations. We will see that the computational requirements of exact dynamic programming are formidable, and for the motivation of approximations if we want to go to problems that are realistic and complicated. Then the second half of today's lectures is going to be on, we're going to start on approximate dynamic programming, and we are going to talk about a technique that's called approximation in value space. Approximation in value space deals with approximating cost functions. Dynamic programming involves sequential computation of cost functions that I'm going to discuss what they are, and sometimes you'll find the name value functions. So what we're going to talk about is approximation of these value functions, and in conjunction with limited look ahead. Okay, I'll explain this terminology a little later, but that's the topic of the second part of this lecture, and only one portion of that, which is based on so-called parametric cost approximation. We have a certain function that we want to approximate. We look for approximations within a parametric class that involve a vector of weights, like in neural networks that I know some of you have worked on. And neural networks provide a parametric cost approximation in the context of dynamic programming and elsewhere. There are also things called features, which work in conjunction with, well, are generated by neural networks sometimes, or work in conjunction with neural networks and other architectures. So we're not going to have enough time to do all this today. I'm going to start on neural networks and then discuss them tomorrow morning in a more complete form. So the second lecture on approximate dynamic programming is going to focus on supplementing the material of the second lecture, and also discuss another major idea in the field: how to control a system of which you don't have a model. No mathematical model. One of the major limitations of stochastic optimal control is that you need to have a mathematical model, a system equation. You need to have probability distributions of the uncertain quantities and all that. It's on paper, but in practice, these are difficult to obtain. Nice thing about this methodology is that it may not require a system model. Instead, it can work with a simulator of the system. In other words, if you have a computer model, it will also work just as well as it would work with a mathematical model. So this is called model-free approximate dynamic programming, and you may have heard the term Q-learning, and all of this is very much an important part of this methodology. There are other things that we're going to discuss: rollout algorithms, Monte Carlo tree search, and in the context of all those, we're going to say a few things about the applications, very challenging applications, very impressive applications in the game of backgammon, which is an old one, it goes back like 20 years, and AlphaGo, which is very recent, it's just 1 year. And the last lecture is going to discuss, the last part of tomorrow's lecture is going to talk about a technique that's a complement of the approximation in value space. It's approximation in policy space. We approximate policies, control functions, not the cost function of a problem. Some ideas are shared between the two approaches, but there are also differences and there are also connections. Anyway, this is in the way of a broad overview, and we're going to give more details later. Okay, so let's say a few things about exact dynamic programming. Now, I know that many of you are familiar with the technique, and so bear with me. We want, among other things, we want to pinpoint the areas where approximations are needed. So we're going to talk about the basic problem formulation, give some examples, and then give the dynamic programming algorithm. And that's it for the first half of today's lecture. We're going to take a break after that and go into approximations. Okay, so we have a discrete time system involving a state at time k, which I denote by xk, a control at time k, which I denote uk, and a random disturbance, a random uncertainty at time k, which I denote by wk. Xk is the state, and this equation describes the evolution of the system. Given the current state, we apply control, a disturbance happens, and the new state, xk plus 1, is generated. Now, the state can be many different things. Given a practical problem, you can consider several different things as a state, but roughly speaking, key to understanding the right kind of state is to find a quantity, an economical quantity that summarizes all the past information that's relevant for future optimization at time k. So roughly speaking, a state is what we need to know to do the best possible for the future. It summarizes everything that's important from the past in a single quantity, which we call state. UK is the control. It's the decision to be selected at time k from a given constraint set that may depend on the current state. WK is a disturbance, an unknown, a random parameter that has a given distribution, a probability distribution that depends on xk and UK. Now, if the problem is deterministic, and there are many problems, many important problems that are deterministic, then there is no WK. Okay, then we have a simpler system, but we are going to talk about stochastic systems, and much of what we are going to say also applies to deterministic. Okay, so you have this system generating states under the influence of control and disturbance, and at each time step, there are capital N type steps, a finite horizon. N is a synonym for, horizon is a synonym for N. It's the number of steps over which control takes place. At each one of these time steps, there's a cost that's being generated. The cost at time gk is a function of the state, the control, and the disturbance at that time. And we accumulate cost over the n time periods additively, and there's also a terminal cost added at the end that depends on xk, the terminal state. Now, if you look at this quantity here that's within braces, it is a random quantity. It is random because the WKs are random and the system evolution is random. So we take the expected value of that in order to associate cost with a number, to give a number to the cost rather than a random variable. So that's what we try to do. We have a system under our choice, our controls, and this is the cost function. And now one more thing, the state space, control space, and disturbance space are arbitrary. There are no restrictions. They can be discrete, they can be continuous, they can be anything. There is no reason for the basic theory of dynamic programming to restrict the character of these quantities. It just makes things easy, and we don't have to deal with issues that are not relevant to the basic concepts. Okay, now what are we going to try to optimize over? We assume that the control is applied with exact knowledge of the state k. Now, system evolves, it can go into unexpected areas that we cannot predict. Clearly, if we know where we are at a given time, if we know the current state, that can be useful information. Therefore, it makes sense to exploit this information and use this knowledge. Using knowledge of the state means that we apply feedback. Here is the setup. We assume that the state at time k is observed by the controller, which is some kind of a mapping that gives us the control to be applied. In other words, the control to be applied is a function mu k, okay? A function of xk. So we observe xk, map it through to control. The system evolves under also the influence of disturbance. The next state, xk plus 1, is generated. Then it is mapped into control again, and so on. So this is a feedback generation of controls, and it gives rise to what we call feedback policies. I'm going to be using the term policies. Policies stand for control functions. They are rules that specify the control to be applied at each possible state xk. Now, there is a control function for every time period, so a policy is this pi that I have here. Mu 0 is the rule that we use at time 0. Mu 1 is the rule that we use at time 1, and so on, up to n minus 1. There is the restriction that the controls should satisfy, the generated controls should satisfy the constraint. We minimize over sequences of functions, not sequences of controls. And this can make a big difference. The difference between feedback control and open loop control. With feedback control, we can do much better. That's the idea here. Okay. Another thing here is, okay, we need to, in infinite horizon problems, this functions mu very often can be taken to be the same for every time period, but for finite horizon problems, this mu depend on k, and not only because, okay, as we get closer to the end of the horizon, we have a different perspective than if we are in the beginning, and therefore we do different controls, but there's another reason. The state space may change from one time period to the next. So we're talking about a very different kind of object, perhaps, for each time period when it comes to these control functions. Okay, so now we want to formulate a legitimate optimization problem. Given a policy, a sequence of functions, and given also an initial state, we plug the policy into the system, and it generates a sequence of costs which are random and depend on the probability distribution of the disturbances. If we take the expected value of that, we get a number that depends on two things. It depends on the policy, and it depends on the initial state. So this j by is a cost function of the initial state, okay? And the optimal cost function is the one that's obtained by minimizing overall policies, this expression. Okay? So that's the optimization problem. It's a formidable optimization problem because we are used to with optimization problems like in linear programming or nonlinear programming or even integer programming, where we minimize over quantities. Here we minimize over functions of quantities. We minimize in a function space, which makes it harder. So that's where we are. System equation, cost function, policies. Cost function of a policy, optimal cost function. And now let's give a couple of examples. Because the state space and the control space and all the other stuff is arbitrary, this is a very, very general problem. It includes deterministic, stochastic problems, and other techniques that I'm not going to discuss. It's a very, very general framework. Any optimization that involves a sequence of decisions with intermediate observations fits this kind of dynamic programming framework. A classical problem of this type is the linear quadratic problem, optimal control problem. It's one of the cornerstones of modern control theory. It involves a linear discrete time system, UK, and A and B are matrices, and the system is generated according to this equation. So xk is the state at time k, uk is a control with no constraints in the classical version of the problem. Wk is a disturbance, a sequence of disturbances that are independent and with a given distribution. And the cost function is quadratic. The cost per stage at time k involves a quadratic in xk and a quadratic in uk. here Q and R are symmetric positive definite matrices. And this, okay, xk is a vector, an n-dimensional vector. X prime is the transpose of that. So this is an inner product like term here. It's a scalar. And the cost per stage is the sum of these two quadratics on state and control. And there's a terminal cost also that is quadratic. Q and R may depend also on K, but I haven't shown this. It turns out that this problem has an analytical solution involving the Riccati equation. There's an awful lot of theory around this problem, many applications. It fits the framework of the basic problem I described because here I have a system, control, all the ingredients are here. Okay, so now let's look at an entirely different type of problem, which is a discrete problem. A problem with discrete state space and discrete number of decisions. This is a deterministic scheduling problem, and it involves 4 operations, A, B, C, and D, and we want to sequence them properly. We have to use all of them. However, there are some constraints. We cannot apply we cannot apply B before we apply A. And we cannot apply D before applying C. And now the order in which we perform these operations affects the cost. And this problem is represented by this tree here. And let me explain. Okay, the circles correspond to partial schedules. So the partial schedule AC involves doing first A, then doing C, and then having to fill up the schedule after that. The partial schedule C means that we start with C, and then what we do after that is open. The terminal nodes in this tree involve schedules where we have scheduled 3 operations, and there's only one left to do, so there's no decision after that. And this circle here is the empty schedule where we haven't scheduled anything. So we also see these numbers along branches. Okay, let's take a branch here that involves the number 3. That means that if we do operation C right after operation A, there's a cost of 3. Here, 6. If we do D after A and C, there's a cost of 6. If we do B instead, there's a cost of 4. Okay? And then at these leaf nodes, there's also these numbers indicate the cost of the last operation. Now, I've deliberately laid out the problem this way. It's a complete description of the problem. All the data of the problem is on the board, and it is in the form where that is involves a discrete time system. It involves the basic framework for dynamic programming. What are the states, what are the controls, and what are the, well, we know what the disturbances are. There are no disturbances. The problem is deterministic. The states are these circles, the partial schedules. The controls are the decisions that we make, the arc that we choose at each state, and the cost of the state is the number that you see along the arc. Now, this problem can be solved by dynamic programming, and I'm going to use it to illustrate the basic idea. That this is, many of you are very familiar with all this, so bear with me. I'm going to go through it as quickly as is consistent with clarity. The dynamic programming idea is, instead of looking at the entire problem, starting from the initial state and examine all these branches that go to the end and picking the best one, it breaks down the problem into smaller pieces, the so-called tail subproblems. We start from the very end. There's a trivial tail subproblem that involves adding the last operation, and we know the cost of that. Then we go backwards, and at these states here, we consider the subproblem that involves completing the last 2 operations. At these states, we consider the subproblems involving 3 operations. And the idea is that by breaking down the problem into these tailed problems, we facilitate their solution. Given the solution of the tailed subproblems of one stage, we can compute the solution of the tailed problems of one stage more, an earlier stage, and we do this easily. We exploit the computation we have done. Okay, so let's look at the subproblems of stage 2. We're going to solve all of these subproblems sequentially going backwards. Here is a typical subproblem at stage 2 that involves starting at the stage CA. We have used operations C and A. And we look at the decisions of that involved here. One is to schedule B, the other is to schedule D. Now, if we schedule B, we get a terminal cost of 1, and if we schedule D, we get a terminal cost of 3. And there is an immediate cost of 2 or 4 here. So we compare the two branches, 2 plus 1 and 4 plus 3. Clearly, 2 plus 1 is better. We record this number, and we have solved the two-stage subproblem. Okay? Now we do this for all of those tail subproblems at stage 2. Here the optimal solution is 9 because there is only one decision. 6 plus 3 is 9. Here 4 plus 1 is 5. 6 plus 3 is 9. It is better to follow this branch here, and the solution of the corresponding tail subproblem involves this branch. So we obtain a solution of all these two-stage subproblems, and we record the corresponding numbers. So now we go one step back. We look at three-stage subproblems, and let's look at a particular state here where we have just scheduled operation C. There are two decisions to make. This one that takes us that schedules operation A. This one takes operation B. It costs 4 and 6. And now, once we get to this state, we know how to do things optimally from there. We have already calculated it, and the optimal cost is 3. So, being at C and selecting A gives us the best cost of 4 plus 3. Being at C and selecting D gives us 6 plus 5, so it is better to select this branch here with a cost of 7, which you see in this green square. There is another problem of this kind, and we have now finished with the stage 1 subproblems, and we go back one more step. The stage 0 subproblem, and it involves the entire problem. There's only one state to consider here. This is the empty schedule originally. We can select A or we can select C, and the corresponding numbers are what you see here. 3 plus 7 is better than 5 plus 8, and the optimal cost starting from the empty schedule is 10. But that's our original problem. So we have found the optimal cost of the problem, and we can construct the optimal sequence by going forwards. We do a computation backwards, we record the optimal decisions at each step, and then we piece together the optimal sequence going forward. Here it is optimal to choose this, we go to C, then it's optimal to choose this, and so on, and this sequence of arcs gives us the optimal schedule. Of course, it's a trivial problem, but think of a situation where instead of 4 operations, we have to sequence 10,000 operations. There's a combinatorial explosion of the number of states as you add more and more decisions. The search space can increase tremendously, and that can be a difficult computation. But conceptually, it's very simple. We break it down into little pieces and go backwards. And what we have done is a manifestation of the so-called principle of optimality, which is the foundation of dynamic programming. Roughly speaking, it says the following. Suppose that we have an optimal policy, which I call pi star, okay, consists of a sequence of control functions mu 0 star up to mu n minus 1. And now let's consider the tail subproblem whereby we are at state xk at time k and wish to minimize the cost to go from time k to time n. So this tail subproblem starts at state xk at time k and goes all the way to the end, and its cost function is what you see here. The costs from k to n minus 1 are included here. Okay, so let's consider this tail subproblem. And we have to start with an optimal policy for the original, and let's consider the tail of the optimal policy for the original. Then the principle of optimality says that the tail of an optimal policy is optimal for the tail subproblem. And otherwise put, if we solve these tail subproblems backward, we don't deviate from optimality, and we construct an optimal policy. Okay, to give you an example of a more concrete example of the idea, suppose I want to go by car from Massachusetts, where I live. I want to go by car to Los Angeles, across country, and I want to find the shortest route. And suppose that this shortest route takes me through Chicago. Then, if I consider the problem, if I consider an alternative, and I take the plane, I take the airplane to go to Chicago, and then take a car, and consider solving the shortest route problem from Chicago to Los Angeles. Then that shortest route from Chicago to Los Angeles is going to be the same as the tail portion of the shortest route from Massachusetts to Los Angeles. Okay, the tail of an optimal policy is optimal for the tail subproblem, and this gives the idea. This underlies the dynamic programming algorithm. We start with the last tail subproblem. We solve the stage k tail subproblems using the optimal cost to go of the stage k plus 1 tail subproblems. According to the principle of optimality, there is nothing lost in doing so. And this is exactly what we have done with this scheduling problem. The optimal value of the 0 stage subproblem is the optimal cost as a function of the initial state, and in the process we construct the optimal policy.
Although this it may not happen to be the optimal policy for the full problem. In other words, the tail. Here, the tail is the same.
We do a lot of redundant computation. We solve all the tail subproblems, and afterwards, after we piece together the optimal policy, we select only some of the tail subproblem. However, to get to stage 0, I have to solve all the tail subproblems. Yeah.
In the previous example, what is the noise? The noise is just 1/4 for A, B, C, D. It's equally probably.
No, this was. Okay, the question is what happened to the noise in this example here? Oh, it's a deterministic problem. Yeah, right. I think I mentioned somewhere here, but it sort of yeah. All of these combinatorial problems are typically deterministic, but the combinatorial that you can have with the increase of the search space.
Because if it's random, then the initial state can change a lot of the results, right? If there's randomness there. Maybe the initial state will forget after some point.
You still have to solve tail subproblems, except that the diagram is not going to be as crisp and uncluttered as it is here, because each one of these decisions, okay, let's say the decision to schedule B, is not going to lead to a unique next state. If, let's say, our schedule is such that, machine shop is such that, and we ask for one thing and get something else, okay? Then there's going to be also a number of possible states that may result from the values of the uncertainty. The next state is not certain, so there's an extra layer and a lot more complication. Okay. But for a deterministic problem, The diagram is simpler and illustrates the idea of a tail subproblem going backwards. Okay, so we went through the principle of optimality, which motivates the dynamic programming algorithm, and now I'm going to give this algorithm. Remember our problem: state, controls, disturbances, system equation, course per stage, and the dynamic programming algorithm takes all this data and computes for all k and states xk the optimal cost of the tail problem that starts at state xk. So at typical state k, there are all these the different values of state. For each one of those, we solve the tail subproblem, and the optimal cost we call jk of xk. It's a function of xk. And the computation is what you see here. This is the dynamic programming algorithm. It starts from the very last stage, the very last tail subproblem, which is just to compute the terminal cost as a function of the terminal state. Now suppose that I have computed jk plus 1, the optimal cost of all the tail subproblems that start at time k plus 1. Then to go to time k, we add the cost of the current stage k, and we add the optimal cost to go from there. Okay, this is a random quantity because of wk. I take the expected value, and I minimize over all uk. Okay, so this is a mathematical expression of what I did in this scheduling problem. We have solved the k plus 1 subproblem, tail subproblem, and then go one step backwards by adding the one stage cost and optimizing over all possible branches which correspond to controls. So that's the algorithm, and this is a correct algorithm for any state space, control space and disturbance space. It holds always, okay? So that's convenient because we don't have to make any further assumptions.
But the expectation should exist. Yes, there should be some assumptions on WKs. I'm sorry, maybe I'm not that familiar with this.
There should be some assumptions. I can sense that you're a mathematician.
Yes, statistician. I prefer
statistician. Yes.
I prefer statistician.
That's even worse. When it comes to stochastics.
Yes.
When it comes to stochastics. Indeed, there are some very, very complicated mathematics here. You have to assume measurability. You have to assume.
But moments. How about the moments of WK?
Right. There could be the possibility that the expected value is infinite. Yes, exactly. And so what do we do then? Okay. All of this can be resolved. And I have spent a good part of my professional life around this issue, and I have sympathy with your concern, because I had the same concerns. After I worked on this and wrote a book with my colleague Stephen Shreve, we discovered that indeed the mathematics were very interesting, rigorizing this kind of calculation. And from a practical point of view, there was nothing to be gained. There was no practical insight that could be obtained by working out the mathematical minutiae of all this. It all worked out as if there were no mathematical difficulties at all. So in this introductory, I'm glad you asked the question, so I had an opportunity to clarify this. But for this introductory lecture, that's way beyond and I can give you references that deals with all the mathematical issues around. Yeah, you're right. The equation exists. Are the cost functions measurable? In order for cost functions to be well defined, and so on. All of these are very important issues from a mathematician's point of view. And incidentally, some of very prominent statisticians have worked on these issues, like Blackwell. David Blackwell, for example, is a pioneer in this area. Okay, so here's the interpretation of the dynamic programming algorithm. Minimize over UK, the k stage cost plus the optimal cost of the tail starts at k state xk plus 1, which is given by the system equation here. Okay, so now once you carry over this problem, at stage 0, the tail subproblem is the entire problem. So j zeros of x0 is the optimal cost function as a function of the initial state, and it's generated at the last step of the algorithm. And if we record the minimizing controls in this equation, which are a function of the state, we construct a policy, and you can prove that this policy is optimal. So we solve all these tail subproblems, and simultaneously we construct the optimal policy this way.
How we assume that the problem is a convex problem, or no?
No assumptions. There is no convexity, non-convexity. Convexity really.
Only the optimality principle has.
Okay, I have cut corners a little bit in my statement here of the optimality principle, but if you think things properly, there are very few assumptions that are needed for this algorithm to be valid.
I resolved the assumptions.
I'm sorry?
I resolved this issue recently, so if you want, I can complete this discussion. It's a couple of things that you have to assume.
Okay, yeah, sure. Okay, now there are assumptions here in order to get sharper results, okay? But this algorithm is valid under very, very general assumptions, but there are perhaps improvements of the basic results can be obtained under additional assumptions, and we can discuss this offline later. Okay, so how do you prove this? There is a proof. It's not, I've been speaking as if there was no mathematical proof of this, but a proof is required, but the proof is relatively simple except for these mathematical niceties and the refinements that we discussed earlier, and the proof is by induction. This is the basic statement. You assume that it's true for time k plus 1, and then you prove that it's true for time k, and you go all the way to 0. The argument intuitively is very simple once you understand the principle of optimality. But there are some mathematical details that you have to look into. Okay, now if you look at this algorithm, there are an awful lot of tail subproblems to solve. Okay, many, many values of state xk, and the computations here can be formidable. So approximate dynamic programming primarily motivated by the often enormous computational demands of exact dynamic programming. The memory of your system may not be nearly enough to hold your problem. The computation may be overwhelming, and so on. So this is my last slide, and then we'll take a break. Before we get into approximate dynamic programming, I want to give you some perspectives. What to expect here, okay? Because there are a lot of claims in the literature, and you have to be a little careful. The first is that in exact dynamic programming and in most of optimization, there is a connection between theory and algorithm. The theory is relatively solid. There are convergence results, the rate of convergence, the results, and so on. There are solid mathematics that tell you what to expect from these methodologies. Programming, the connection between theory and algorithms is fragile. It's not that there does not exist theory. There is theory. However, the theory is not always very good at predicting what could happen. Moreover, there's a great variety of approximate dynamic programming approaches. Some approximate dynamic programming algorithms have been able to solve impressively difficult problems, but have failed in other problems. We often do not understand the reasons, and of research that's ongoing to understand for what kind of problems different approaches may work. There are tremendous success stories that don't have any theory behind it, or have a limited theory behind it, not a complete theory behind it. There are some theoretical results, but no success stories, because there are other problems other difficulties that you may have. including a large computational great computational difficulties. The theory that's available involves assumptions. It's interesting, but it may involve assumptions that are not satisfied in practice very often. So, okay, it's good to know theory because it guides the intuition, but theory is not enough to guarantee you good results. There's an element of art in all this. And the challenge is how to bring to bear the right mix from the broad variety of methods and theoretical ideas, how to bring them to bear on your problem with its own characteristics. So I'm going to, with this, we're going to discuss some of the approaches that have been used in this context. The payoff is potentially very high. There is a lot of room for creativity, but there's no guarantee for success. There are no guarantees. In love, war, and approximate dynamic programming, there are no guarantees. So let's leave it at that, and we'll come back. I don't know how we're doing with time.
It's, let's say, 5-minute break.
A 5-minute break would be fine, yeah.